So today we will be discussing how to find the shortest distance in an undirected graph, as well as there will be no weight that will be assigned to the edges, right? So assume that this is the graph and the adjacency list for the given graph will be something like this that I've already drawn, as because I've already discussed in the previous videos how do you get an adjacency list for a given graph. So whenever there is an undirected graph and there are no edge weights, we always assign 1 to the edge weights. Yes, just assume that all the edges are weighted as 1. So that is the assumption that we always take if it's an unweighted graph. And the problem statement is very simple. You will be given a source, right? You will be given a source. So let's assume that the source is 0 and you have to find the shortest distance from this node 0 to all other nodes. For an example, if I want the shortest distance from 0 to the node 6, so what is the shortest distance? You're going to say that you're going to take this path, right after that this path, right after this path. So there will be 3 edges that you have to cross. So I can say that the distance, the shortest distance is 3, because if you take this path, this is going to be 1, 2, 3, 4. So I can definitely say that the shortest distance from the node 0, which is our source node, is definitely 3. So this is 0, which is always the source, and this is the destination. So the shortest distance between this source and this destination is 3. So the problem statement is very simple. You will always be given a constant source. Now this is the source that is given to you, and you need to figure out what is the shortest distance from this source to every other node, be it a one node, be the node 2, be the node 3, be the node 7, be the node 8. You have to find the shortest distance from 0 to every other node. That is our problem statement. So in order to solve this problem, we are going to use the BFS algorithm, but yes, we will be doing some modifications to the BFS algorithm. So if you don't know what is this BFS algorithm, you can watch out my previous video where I have already explained what is BFS algorithm. So initially what you will do is, you will take a distance array, right? Let's take a distance array initially, and it will be of size similar to the number of nodes. So I can declare it of size 0, 1, 2, 3, 4, 5, 6, 7 and 8, because I have at total 9 number of nodes. And make sure that everything is marked as infinity. So let's mark everything as infinity. Now when I say infinity, you can mark it as int max, you can mark it as 1e9, you can mark it as 1e18, depending on your constraints you can mark it. So I'm gonna mark it as infinity as of now. Infinity can be anything, I'll be repeating this, and this will be your distance array, remember this. And along with this, take a queue data structure. Yes, take a queue data structure, and this queue will always store, remember this queue will always store the nodes. This queue is going to always store the nodes. So at the first step, what you're going to do is, whatever is the source node, remember this, whatever is the source node, just don't think anything, just take this source node and put it into your queue. And with this, please make sure that you mark distance of 0 as 0. Why do you do that? Because you know, if you want to travel 0 to 0, like from the node itself to itself, the distance taken will definitely be 0. So I'm marking it. So this is your initial setup. You're gonna take a distance array, mark everything as infinity apart from the source node, and you're also going to take a queue data structure. Yes, a queue data structure which always follows the first in first out technique. So you're going to take a queue data structure and you're going to put the source into it. Now at first, whatever is there on the source, you take it out. So the node 0 will be taken out. So let's take the node 0 out. So whenever you take the node 0 out, you always know that the distance, yes, the distance to this node 0 is nothing but the distance stored here. So I can say the distance as of now is 0, because to reach 0, we have taken a distance of 0. Now the next step, you check out what are the adjacent nodes of this node. So I see the adjacent node is 1 and 3. Now if just think on this, if there is a node 0 and you're taking a distance 0 from the source, because as of now I'm just thinking that it is a source, I know it is 0, but think it as a source. The source has taken a distance 0 to reach 0. The adjacent node is node 1 and the adjacent node is node 3. So can I definitely say, if you add a plus 1 to that, that will be the distance that you will take to reach the node 1, and that will be the distance that you will take to reach node 3. So I can say that, okay, to reach the node 1, I'm taking a distance at a total of 1, which is better than this infinity. So let's replace it. So whenever you replace this, you take this node and you put it into your queue data structure. Similarly, for the node 3, if this 0 and plus 1 is taken, the total distance to reach 3 will be 1. So just go to 3 and replace that with the help of a distance 1. And whenever you replace it in a distance array, that means you got a better solution to reach this particular node, that is node 3. So just put that node into your queue data structure. So once you have done for all the adjacent nodes of this given node, yes, of this given node, you can say your task is done. Now in the next iteration, you can take the next node. Yes, what is the next node? The node is 1. What is the distance that you have already taken? The distance taken can be found out by the distance array. The distance taken is 1. So again I can say, to reach node 1 from the source, I've taken a distance of 1. Now what are the adjacent of 1? I can say that the adjacent of 1 is 0, the adjacent of 1 is 2, as well as the adjacent of 1 is 3. So if you want to reach 0 from 1, that means there will be a addition of an edge, so that will add a distance of 1. So I can say that the total distance taken will be 2. Now let's check out what is the minimal distance to reach 0. The minimal distance taken to reach 0 is 0. So will you consider this 2? The answer to that will be no, because it is not the minimal distance. I'm just applying a greedy algorithm of checking. Now this will take a distance of 1. So if you add 1 plus 1, this will give you a distance of 2. So will you now take the distance 2? The answer to that will be yes. Why? Because to reach 2, previously you were taking infinity. Now you are taking the distance 2. So let's take it. And since you have taken this, just take this node 2 and put it into your queue data structure. Right? So once you have done this, you can go to the next node, and that is the node 3. So when you go to the node 3, you know that will again take a distance of 1. So if you take this up, the total distance will be 2. So will you take this? No. The answer to that will be no. Why? Because the distance to 3 is 1. Again, that's very obvious, because if you take from 0 to 3, the distance will be 1. And if you go via 1, that is this path, the distance is going to be greater. So we do not consider the other path. So we will not take this. So as we see for this node 1, we have tried out all the adjacent nodes, and we just found out node 2 that was inserted into the queue. So I can say my task for the node 1 has been completed, and I will move to the next node, that is the node 3. So the next node is node 3. So let's take the node 3. So let's check out the distance to node 3. So you can get that from the distance array, that is the distance 1, right? Now what are the adjacent nodes of 3? That's very easily 0 and 4. How do you get this? From the adjacent matrix or the list. So you get the node 0. So if you get the node 0, what will be the distance? This will be 1. So the total distance will be 2. And over here, you can see that the 0 has a distance of 0. So you will not consider this distance 2, because that is not a minimal distance. Now at 4, if you want to reach 4, you will take a distance of 1 from here, and the total distance will be 2 to reach 4. Now will you take this into consideration? Yes, you will, because to reach 4, you were previously taking infinity. Now you are taking the distance 2. So let's take this into consideration. And whenever you take something into consideration, put that into your queue data structure. So you did put 4 into your queue data structure. Now does node 3 have any other adjacent nodes? No, it doesn't have anything apart from 0 and 4. So I can say my job is done for the node 3. So I can move to the next node, that is the node 2. So let's move. So next we have the node 2. So let's take the node 2. What is the... So the next node is node 2. And I can see that from source, the node 2 is taking a distance of 2. You can get it from the distance array. So let's have the distance 2. Now where can node 2 go? Node 2 can go to its adjacent nodes that are 1 and that are 6. So if you decide to go to 1, so can I say the total distance taken will be 1? And to reach 1 from this source, it will go via 2. It will take a total distance of 3. But to reach 1, you're already having the distance 1. So this will definitely not be considered. to reach 6, I can say this will take another distance of 1 and the total distance will be 3. So will you consider this? Definitely yes, because 6 is taking infinity. So let's consider this 3. So if you consider this 3, you can write it over here. So the node 6 has been written here and the distance 3 can be written here. So you have reached node 6. Now can I say the node 2 has completed all its adjacent node traversals? So I can just move to the next node, that is node 4. So the next node is node 4. So when you write the node 4, so I'll just be doing it quick. So if you write node 4, the distance of 4 is 2. What are the adjacents of 4? 3 and 5. Now if you add these two guys, the distance will be 3. For 3, the distance is already 1. So this is not going to be considered. For 5, the distance is definitely 3. Will it be considered? Yes, it will be considered this time. Why? Because for 5, the distance is infinity. So I can just rewrite it to 3. So I can say this node was rewritten distance from infinity to 3. So let's take it and put it into our queue data structure. So again I can say the work for node 4 has been completed. So let's move to the next node. What is your next node? That is the node 6. So in order to reach the node 6, what is the distance taken? You can again get it from here. Distance of 6 is 3. So I can say it's a 3. So what are the adjacent nodes of 6? That's 2, 5, 7, 8. You can again get that from the adjacency list. In order to reach 2, you'll require another distance of 1, which makes it a total distance of 4. Now will you take consideration? No. Why? Because 2 is already having a distance of 2. So I don't have a better solution. So I'll not take this into consideration. Will you take 5? Let's see. 3 plus 1 is giving you 4. So will you take this into consideration? 5 is having 3. Why will I take a path which is giving me a distance of 4? We will not take this. Will you take 7? So I see the distance is 4 and I see 7 as the infinity. So I'm reaching 7. So I am definitely going to take this path. The 7 will be taken and put into the queue. So you take 7 and put it into the queue. Let's check out for 6. For 6, if you want to reach 8, the distance again will be 4 because 3 plus 1 is 4. For 8, it was infinity. So again I can say I'll take a path which is having a distance 4. So since you took out 8, you'll take it and put it into your data structure. So in this way, you got all the adjacent nodes of 6 covered. So now let's move to the next node, that is the node 5. So you have a node 5. So in order to reach node 5, what is the distance that you will consider? That is nothing but distance 3. What are the adjacents of 5? You can see the adjacents of 5 are 4 and 6. So let's write down the distances, that is 1 and 1. So it will have a total distance of 4. This will have a total distance of 4. And you can see both of them will not be considered because at 4 you had a distance of 2. At 6 you had a distance of 3. So both of them will be not considered. So the node 5 is over. Next you will get the node 7. So for 7, if you figure out the distance, that is 4, 7's adjacent node is nothing but 6 and 7's other adjacent node is 8. So if you try to figure out the distance for 6, you will get 5. Again, that will not be considered. For 8, you will get 5, which will again not be considered. So for 7 also, none of the nodes will be considered. So the node 7 is done. Let's move to the next node, that is the node 8. The node is 8. That is the next node. So again, if I write it, the distance of 8 is 4. What are the adjacents of 8? 7 and 6. If you carefully observe, 7 and 6 are the adjacent nodes. So if I write the edge distance, that is 1, that is a 1 over here. So if I again write the total distance, it will be 5. For 7, I already have a 4. So this 5 will not be considered. For 6, what is the distance? Total of 5. For 6, I already have a 3. So this will also not be considered. So I can say I did check out for all the adjacent nodes of 8. So the task for 8 is also done. So once you have done for all the nodes, you can see that the queue has become empty, similar to BFS algorithm. So once the queue is empty, you can say that this distance array is definitely storing your shortest distance from the source that we assumed to be 0. Yes, we assumed the source to be 0. So this distance array will be containing the shortest distance from 0 to every node, like from 0 to 0, that is 0. From 0 to 1, that's 1. From 0 to 2, that's 2. From 0 to 8, that's 4. So every shortest distance is in this distance array. So what is the time complexity for this algorithm? Now, since you're implementing a BFS algorithm only, just we are modifying it. We can say that the time complexity will be the number of nodes plus the number of edges. That is the time complexity. What will be the space complexity? Apart from this adjacency list, the space complexity that we are using is definitely big O of n plus big O of n, because we are using a queue data structure as well as a distance array, and there is no auxiliary space. So this will be the overall time complexity and space complexity in our BFS algorithm that we are writing in order to find the shortest distance in undirected graph. Now what is the intuition behind this algorithm? Now you know what is a BFS algorithm. BFS always visits the node in sequential manner. This is at a distance 0, so BFS will make sure it visits it. Then BFS will visit this and this node. So it is visiting in sequential manner at equidistance, like at equidistance. If this is at a distance 1, this will definitely be at a distance 1. After that, it will visit 2 and then 4. BFS is this only, right? It visits nodes in parallel. Like if they are in the same level, it will visit them. So I'm very much sure if I implement the BFS algorithm, I will reach the node at the shortest distance only. That is why the BFS algorithm does work when made some modifications. So let's discuss the C++ solution to the algorithm that we just now discussed. So we have an adjacency list, we have the number of nodes, as well as we have the source. Now what did we do at the first time? We had a distance array, everything marked as infinity. So let's mark it as int max. You can mark it as 118, that's your wish. I'm marking it as a very big number. Right after that, we always had a queue. So we have taken a queue. And what is the initial thing? We always took the source, right? The source has been taken. So we marked the distance to source as 0. And we also added it to our queue. So that was the thing that we always did. After that, the iteration went over. The BFS algorithm will always go on till the queue is non-empty. So let's have the BFS algorithm till the queue is non-empty. Whenever you're doing the BFS algorithm, what is the first step? Get the node from the queue and take it out from the queue. So you have got the node from the queue and you have taken it out from the queue. After this, what did you do? You traverse for all its adjacent node. And what was that you were always doing? You always did a check. If distance of node plus 1, yes. If distance of node plus 1 is lesser than distance of IT, that means you're currently at a node, right? So it would have taken a distance. If that distance plus 1, because there's an edge, plus 1 for that, if that is smaller than distance of IT, yes, if that is smaller, that means to reach that node IT, you have got a better path. So let's replace distance of IT by that new distance that we did while explaining. Once you have done this, whenever you replace the distance, you just take that distance and put it into the queue, if you remember. So I just took the distance and made sure that that was put into the queue. So once this is done, and once this is done for all the nodes, the queue will be empty, right? As you did see in our example, the queue will become empty. Once that has become empty, you can print all the distances, and that will be the shortest distance from this given source. So this will be the C++ code where the BFS algorithm has been slightly modified. So it's time to discuss the Java code. Now you can see that in the Java code, in the function, we have the adjacency list, we have the number of nodes, as well as we have the src, which is the source. So what we initially do is we make sure that we have a distance array, right? That is the first step of size n. After that, what we do is we have everything marked as a very big number. I'm assuming this to be the infinity, so let's mark it as a very big number. After that, we always required a queue. So have the queue data structure ready. And whenever you started, what was the first thing? The first thing was the distance to source itself will be 0. And the queue will have the starting source, right? Queue will always have the starting source. So these two things are done initially. After that, the BFS algorithm will be in function till the queue is not empty. So we'll run this BFS till the queue doesn't becomes empty. Now every time we get the node that is at the top of the queue, right? That is the first inserted node. We get it from the queue. Once we get it, what did we do? We traversed for all its adjacent node, if you remember. So let's traverse for all its adjacent node. So we are going to traverse. Now if we know till the distance, till the node, the distance is distance of node plus 1 for the new edge to it. If that's smaller than the previous distance that we have got, if that's smaller than infinity or something else, what we are going to do is we're simply going to reinitialize distance of it by that new value, and that's nothing but distance of node plus 1, as we did in the explanation. Once you have done that, whenever you reinitialize distance, you take that node and you make sure that that is added to the queue. So once you do this for all the nodes, yes, once you do this for all these nodes, queue will be empty, and you can say that this algorithm is over. Once that is over, I can simply print all the distance, because they will be the shortest distance from this source to any given node I. So this will be the Java code. So guys, I hope you have understood the entire explanation. So just in case you did, please make sure you like this video, and if you are new to our channel, please do consider subscribing to us. And yes, with this I'll be wrapping up this video. Let's meet in the next video, where I'll be discussing the next algorithm from the graph series.
Whenever your heart is broken